Good evening guys, welcome to lecture 1.1 of unit 2, nuclear stability. Let's get started. Here are the learning intentions and success criteria for this chapter. Please pause the video and attempt to complete the knowledge and skills table. Okay, so having looked through here, hopefully you identified a few of the following. In terms of knowledge, we need to be looking at firstly, well, what is an atom made up of and how is it organised. So we need to know its structure, we need to know its composition. The second thing we should know about, well, is what is an isotope. If you don't know what an isotope is, it's very hard to identify one. And finally, we need to know, well, how are different atoms stable or not, because we need to explain what causes stability. In terms of skills, well, this isotope identifier here, we need to know, can we actually recognise what these actually look like? And so then you can interpret the information that is contained within an isotope name or an isotope symbol. So this video is going to encompass topics discussed in chapter 4.1 and 4.3 of the unit 1 and 2 textbook. 4.2 will be covered a little bit later on. It's been placed a little bit earlier by the author. However, we're probably not going to need this information through the next through chapter 5, and we'll come back to it when we get to chapter 6. Okay, so let's start off with the idea of a nuclear model. So back in grade 9 we taught you about the structure of an atom, and it looked kind of like this. So we've got our protons and our neutrons here in the middle, and then we've got our electrons around the outside of it, and we can see them here. They are in these shells or energy levels. So here's energy level 1, here's energy level 2. This is a carbon atom, so it only has 2 energy levels, but if it was something bigger like a uranium atom, we would have 4, 5, 6 energy levels. If you do chemistry, you may have some knowledge about electron shells in terms of orbital structures like S structures, P structures, etc. You don't need to worry about those this year for physics at all. If we look at these, we can see that the protons and neutrons are actually a lot bigger than the electrons. So this picture here, it is drawn not quite to scale, not the slightest, and most drawings of an atom are not drawn to scale in the slightest either. So these protons and neutrons are about 1,000 times bigger than the electrons around it, and they make up most of the mass of an atom. Even if you had something very large like nihonium with 113 electrons, this would only account for about 10% of one proton, so they are quite small. There is a table on page 137 of your textbook that is missing the powers for the masses, so here are the corrected values for that. You can see they do have the first part of it correct, 1.6726, though there's, I believe, goes to about 6 decimal places. And however, they are forgetting the powers there, and so you can see by looking at the powers, 10 to the negative 31 compared to 10 to the negative 27. There's a 10, 1 times 10 to the 4 there that it's kind of off by. Recall that these protons do have a positive charge. That is important to know. I always remember it as P for proton, P for positive. Neutrons are neutral, meaning they have no charge, and electrons are negative, and this was a convention decided by some early work on electricity. So for every single proton, an atom gets a +1, for every electron the atom gets a -1. The textbook goes into a little bit about electrons and ions, however that's more of a chemistry thing. You do need to be able to recognise it, but it's not something I'm really going to cover very much because it's something you've done in chemistry for the last couple of years. Okay, now protons and neutrons are the important bit for nuclear physics. So the number of protons in an atom is very important, and you should recall that the number of protons makes an atom what it is. Number 1 is hydrogen, 6 protons gives you carbon, 8 protons gives you oxygen, 92 gives you uranium. You add a proton, you change what it is, you take away a proton, you change what it is. And you can find those on the periodic table. This is an excerpt from your periodic table you will have in your data booklet. And you can see here there's an atomic number at the top, number 1, that tells you how many protons are in this element. You can see here hydrogen has an atomic number of 1. A couple of other things there, we'll go into that shortly. Now, the number of neutrons, though, tells us what an isotope the atom is. So protons and neutrons are together called nucleons. Any subatomic particle in the nucleus is called a nucleon. These are the protons and neutrons. And that nucleon count is part of an isotope's name. So So if we take carbon, carbon is element number 6. If you look in your periodic table, you can see it there. It has 6 protons. It's got a average mass of around 12.001 or 0.011, but most carbon that you find around us, the stuff that's in us, is mostly carbon 12, and so it has 6 protons and 6 neutrons. If we count them up, you can see 6 plus 6, 6p, 6 protons plus 6n, 6 neutrons, gives us a total of 12, and so the isotope name is carbon 12. Carbon with 8 neutrons instead, 6p because it's still carbon, plus 8 neutrons is 14, is carbon 14. And you may recall that that is the radioactive form of carbon 14, carbons that is commonly in us. Now this one can also be written as C12-6, and this one will be written as C14-6. Whether an isotope is written in name form or this AZE notation, you are expected to be able to work out, well, what is the number of protons, what is the number of neutrons from it. Now, finally, when we deal with a word called isotopes, so I said that earlier, an isotope is chemically the same no matter what form it is. So carbon 12, carbon 14, to a chemist, they are identical. But they will have a different nuclear stability. Some isotopes are stable, some isotopes are not stable, which means that they are radioactive. And each of these isotopes is called a nuclide. Okay, a particular isotope, so we say the carbon 12 nuclide or the carbon 14 nuclide, and that word will get used a bit in your textbook going forward, so just be aware of that language there. So when we talk about atomic mass, the masses are very, very small. We saw that before, negative 27 kilograms for one proton, negative 31 for one electron. However, so because of that we use a different mass, it's called atomic mass units. Now over time we've gotten some pretty good measurements of it. Originally it was a mass of 1, because why not? But over time we found that carbon weighs this much, but the mass of the proton or neutron is actually this much. And so the protons and neutrons have changed over time, and this is the values that will be provided to you on on your data booklet. So the proton has a proton mass of 1.007276 U. That's the unit for atomic mass units. And you can see the neutron is 1.008665. So it's a little bit fuzzy there. You do have to use that level of precision, because otherwise, if you round that off to 2 decimal points, proton would be 1.01 and neutron would be 1.01. And because you're going to be dealing some really fine detail level calculations with these, you do have to use all the significant figures you have there for your protons, neutrons and electrons. Okay, so just be aware of that. Write those down somewhere. They're given to you in your exam and they're in your textbook, but when you do a lot of these calculations with nuclear physics, having these around quickly can help just to speed up your work. Now finally, you've got your atomic mass down here at the bottom, and you can see it's called relative atomic mass on the periodic table. This comes from relative proportions of the isotopes, and this is something that chemistry deals with. We don't need to care about it too much for the syllabus. The textbook may have some questions on it, and it's not particularly difficult for you to work out using the example that's provided. However, it's not something that's part of our curriculum, so it's not something we really need to worry about. So far we've talked about the model of an atom. We've got electrons around the outside, protons and neutrons on the inside. We talked about their charges, we talked about their sizes, and we talked about this idea of isotopes in terms, or nuclides and isotopes in terms of how many neutrons there actually are. But if we go back to thinking about our nuclear structure, there is, apologies, that should have been animated. We know that the nucleus, there are positively charged protons and neutrally charged neutrons, and if we remember back to year 9, we discussed that positive things repel each other, and it's similar to identical poles on a magnet. You try to push 2 north poles together, you can feel them push apart. So if all these positive particles are clumped together, what stops them from being pushed apart? And we now know that it's neutrons that play a role in keeping the nucleus stable. The neutrons act as a spacer for the protons, and you may have seen in that class activity that we did that the ratio of neutrons to protons for a stable isotope is always at least 1 to 1, and most often greater than 1 to 1 once you're past about element number 20. There is something though that is causing this bonding to happen with these neutrons, and that's called the strong nuclear force. It's like a nuclear glue inside the nucleus. Okay? It is one of the 4 fundamental forces of the universe, and it binds any 2 nucleons together. It can be a proton, it can be a neutron. They just have to be close enough and they will stick together. It is much, much stronger than the electromagnetic repulsion at certain distances. So this is an interesting graph from the text, and this is something that I would probably expect to see on an exam, or something that I'd expect you to be able to draw in terms of meeting this criteria, being able to describe, how the strong nuclear force it plays a role in keeping the atom stable. As you can see here, in terms of force, we've got either side of the zero line. On this side it says it's attractive, this side it says repulsive. Could have drawn that the other way, wouldn't matter. And we see here the blue line is the strong nuclear force. So when we're at this very large distance, proportionally very large, of around 4 times 10 to the negative 15, this is around the femtometer scale, so it's quite small. The strong nuclear force is pretty much nothing. But then, as soon as you get around the point of about 2.3 here, 2.2, it starts to increase, and increases very, very quickly until we are around 1.3 times 10 to the negative 15 femtometers. 10 to the negative 15 meters, and then it's very, very attractive. If we look at the electrostatic force, so this is the interaction between a positive and a positive, or a negative and a negative. See here, it's pretty weak as well, slightly repulsive, but still proportionally weak. And as we go here, it gets closer and closer and closer. It's an inverse square relationship here, very similar to the gravitational equation we've looked at. The electrostatic force between 2 things is equal to Coulomb's constant Q1 Q2 over R squared. This is a constant. These two are the size of the charges, and it's this R squared here because we're talking about a radius, and we can see that as this increases it drops off very, very quickly. And if you think about that, if I was to keep increasing R and dividing by bigger and bigger numbers, because it's going to be squared, so it's going to get very big very quickly, it would get very small very quickly. But then as we get below 1, it starts to rocket up really quick here. But then the strong nuclear force is very, very weird. It doesn't have a nice, neat law that allows us to, like the electrostatics or the gravitational one, that allows us to just model out this curve. This is sort of more experimentally determined. After it gets past this optimal point, it then starts to get weaker and weaker and weaker until probably around here-ish, where this is pushing and this is attracting and they're about balanced. But then it gets less, and then it becomes repulsive. So this strong nuclear force, depending on where you are, will either push you away or pull you closer. And it's got kind of a sweet spot here. So if you're in the right spot, it wants to hold you there. You get too far away, it pulls you back. It gets too close, it pushes you away. But if you are not close, if you're too close, it shoves you away quite violently until you're back to the sweet spot. And over here, it just doesn't care at all. Okay? In contrast, electrostatic force is just a constant. Yep, closer you get, the stronger I get. Further I get, the weaker I get. And it's the balance between these two things. Now, up here, the strong nuclear force is 0, but the electrostatic force is not. So the electrostatic force will act at a distance forever and ever. It doesn't have a limit on it. The strong nuclear force does basically have an effective limit in terms of distance. So inside an atom, this is what we call here the typical nucleon separation. So from here to go 2 or 3 nucleons away, so if I just go back to my pen, if I have 2 positives next to each other, well, we've got this. But this positive over here, these 2 will stick and these 2 will stick, but these 2 would flat out hate each other because they are too far apart. Their electrostatic force, yep, that's fine, but their strong nuclear force just doesn't exist between those 2 on the outside. And if you have enough of those, then you end up with a bit of a problem because they just keep pushing and pushing and pushing. Okay. Finally, and this is a lovely webcomic called Saturday Morning Breakfast Cartoons. This may help you understand the strong nuclear force a little bit. So protons go away until they get close enough, and then they love each other. And there's a little bit of a jab against socially maladjusted physics undergraduates in terms of how we understand relationships. The last thing I want to talk about in this is stability. So this balancing between electromagnetic repulsion, the push between protons, and the strong nuclear attraction, the connection between adjacent nucleons, determines an atom's stability. Now this graph, there's a less fuzzy copy in your textbook. This graph shows different isotopes coloured by their stability and the numbers of protons and neutrons. So up the middle of the graph you can see there's a very dark band going up here, and this is the stable band. Okay, and so you can see there is this like little ridge of stability right through the middle. There is this line here, Z equals M, and Z in this case is the atomic number versus the neutron number. And remember, atomic number is the number of protons as well. Across the bottom there we have number of protons, up the y-axis we have the number of neutrons. You can see at the bottom the black line from stability and the Z equals N line, where number of protons and number of neutrons is identical. But the stability bit never actually drops below this value. Sometimes pops a little bit above, but never drops below until it gets around mid-20s, perhaps 30s, and then it starts to creep up quite a bit. You can see it's deviating away from the Z equals N line. So basically you can always have, you can get stability, but you got to have enough neutrons to counteract the number of protons you have. You can see there are a lot of these isotopes around here and here. They are very unstable in terms of, because these darker blues are around the 1 to 100 second range. These lighter blue ones are a little bit higher, while these very pale ones on the outside are just dying in a fraction of a second. There is some thought that, so if we get to here, we see there's kind of a jump where there's no real stable bits in here. Then there's a little bit of stability, not great. I mean, it is still around the 10 to the 8, 10 to the 16 sort of region there, and with those few red ones. So it does mean it decays, but it's reasonably stable. I wouldn't want to use it for anything in the home. Uranium, for example, has a very long half-life, but it's still radioactive and still kills people. So just because something has a relatively high stability doesn't mean it's safe in the slightest. There is some thought that, say, after we get past here, we see there's another little break where there's just nothing stable, but there might be another bit up here. They call it the island of stability. This graph I've also seen drawn the other way around, with the x and the y-axis flipped. So that could be a perfectly valid way of presenting the data. There's nothing that says the number of protons has to be on the x-axis for this graph, and so that's something that you may see in your final exam, where they get you to talk about this graph in terms of stability. Okay. So that's the end of this first video introducing this topic. In the video we have done the following. We've revised the structure of our atom, we've discussed isotope names and the connection to atomic structure, and we've examined the stability of the nucleus and the importance of the strong nuclear force. For your entrance to class, please complete questions 1 to 5 in chapter 4.1 and questions 1 to 6 in chapter 4.3 in the Check Your Learning PDFs. Copy your answers for these into the 2.1.1 space on eLearn. So we are into Unit 2 here, so we'll be back to topic 1 of Unit 2. I know it might be a little bit confusing to start off with, however, please look under the right area. We're no longer doing motion, we're into our next unit. Okay, thanks very much for listening, have a good evening, bye.